Hello, 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 hello. Hey guys, welcome back to my channel. So, so I already called. Yeah, hello, 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 hello. Yeah, we are live, guys. So today I have already called it a day, right? But as went to the bed, then I thought, why not tune to the Acharya Prashant session? But, like after listening him, I thought, why don't I should give one more try to this day, right? Even I see that person was like doing session for all of us at 2 a.m., right, at 2 a.m. in the midnight. Like he don't need anything from the persons that they are which are present right there, but like he's doing for the sake of his for everyone. Like he want to be, he want us to be better, right? So that's why I thought, why not to give one more try to this thing. So today we are going to solve some PYQs, and I earlier have thought that I will solve it once by myself, and then try to explain on the session, as I have OPB coming shortly. So I was preparing for that. Like, yeah, let's solve some questions. Okay, what is the role of the regularization term in regression? Like, so for the ridge regression, you must recall that the idea of the ridge regression is to like to bring down the coefficient, of W closer to closer to zero, in order to avoid in order to penalize the large coefficient. For the solution of ridge regression, we do not want to have very large coefficients in the W vector. That's the idea of ridge regression. And for the if you want to think about the like where the solution of the W will be present, so it will be on the verge of the like circle, right? From the center, I think you should be familiar with this. Let me just a second. Let me open. Yeah. So like uh, first of all, let's see the question options. So it is telling that like it ensures that the data is normally distributed. No, there is no such description of this normally distribution of the data set, right? The data set is given to you, and we are not manipulating the data. So this is wrong answer. Now, it penalizes large coefficient to reduce overfitting. Yeah, the idea of the regression is to reduce overfitting only, but how they are the how region lasso differs is like ridge brings the coefficient closer to zero, while lasso works on the principle that it tries to bring every coefficient exactly to zero. Not every coefficient, like uh, the maximum number of coefficient. What I mean to say is like, say, let's say let's say this is your W vector. Right? Let's say this is your W vector. The idea of the regression is sorry. The idea of the ridge regression is to definitely this W will have D cross one, D cross one, right? D cross one component. So the idea of the ridge regression is to bring all the components closer to zero. Like suppose this component is like 7.3, 2.1, and say minus 1.5, right? So ridge regression will try to bring all these coefficients closer to zero, like 0.014 something of this sort, and 0 point maybe like 1.5. I think you got the idea. So this just simply this coefficient will be bring closer to zero. That's the point of ridge regression. And in case of lasso, for lasso, it will try to bring it will try to bring some of the component to exactly zero. Like it may bring like this component is zero, or this component is zero. It will all the components will not be exactly zero, but most of the component lasso will try to convert it to zero. That's the point. Okay, so we are asked for rigid regression. So it forces the coefficient to be exactly zero. This condition is for lasso regression, and it definitely penalizes large coefficient. This is the concept of regression only, and it increases the variance of the model. Like no, there is no such description of increasing the variance of the model. There, this is only the concept of regression. Like it will penalize the coefficients. In fact, penalize the higher coefficient or larger coefficient. That's the point. Now, which of the following conditions must be satisfied for a decision tree to be pure at a given node? Okay, so while solving a question for decision tree, you should recall that like a node will be said to pure if the impurity is zero, right? And when does a data set is said to be pure? Like if the means if the node that we are considering is see, here will be some question, and this is my first node. If it evaluates to true, then it will point to this box. If this question evaluates to false, it will point to this box, right? Now here we I have pure data set, and here we will have the yes, and here will be a the no, right? Now for this data set to be pure, either it should have like all means every sample that is present here, say x1, x2, dot 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 xn, all the data sets that is present here must have the same level. Either all should be 0 or all should be 1. Like here is 1, 1, 1 and so on to 1. Like this is one case of pure node, or this all thing could be 0, means all the level could be 0, 0, 0, 0. Like this is the case of pure node, right? Okay. Entropy. Now remember, entropy is the measure of impurity. Like if uh, so higher, so like if impurity, the impurity, so the higher the impurity implies higher the entropy, higher entropy. Why? Because this impurity is nothing but a measure of, sorry, this entropy is defined to measure impurity only, and if they are, and they both are directly related, right? Higher the increase in the entropy value will corresponds to increase in the impurity. So the so we have pure node, right? Pure node means every label should be either 0 or 1, and we know that the entropy curve, like the entropy curve is like this. Here the number of ones, here the number of ones is 0, and here the number of ones is 1, and this y-axis is the entropy. Entrop Yeah. So this is the entropy function, and this represents the number of levels that is labeled as 1. This represents the number of, means this axis represents the number of labels or the data points have value 1. So if like if we have 0 if we have no such data points, means if we have all the data points labeled as 0, then it will be pure. In that case the impurity should be minimum, that is 0. And the other case is like when all the labels are 1, in that case also the impurity should be 0. And you could notice that there is a symmetric curve, like, and when does the impurity will be highest? The impurity will be highest when like there is a kind of 50-50, 50% of the data sets are labeled as 1, and 50% of the data sets are labeled as 0. In that case the entropy will be the highest. So we have asked for the pure node, right? Like pure node is there, which means impurity should be lowest, or impurity equals to 0, which means entropy is 0, right? So entropy should be minimum, like this is the minimum. Yeah, so entropy of maximum is wrong. The information gain at the node is negative. See the information gain, if you try to understand the range of the information gain, then you will notice that information gain could never go to negative. It will be always be either, it will always be either greater than or equal to 0. Why? Like information, the formula of information gain is like we have the original data set minus, there is some parameter, say gamma of sorry, this is entropy of, this is entropy of original data set minus, there is some weight associated with the ds, entropy of ds plus 1 minus gamma times uh, entropy of d node, right? So this is the formula. Now if you notice that, then the entropy of this factor, like the data set entropy of the data set means entropy of the actual data set will always be greater than or equals to the entropy of the child nodes. Why? Because you think now, like you have a data set, and then you have a data set, then why you are like further classifying it? Because it is impure. uh, so as the original data set is impure, then in that case the entropy for a data set should be higher, right? See what I'm let's say this is my decision tree. Now I have some data set in here, and I want to further classify it. So first of all, why I will classify if it is completely pure? I will not classify. So there must be some impurity, and that's why we are deciding to further classify, right? So here there should be more impurity as compared to this, the combination of both. This is like very intuitive also, and further we are like uh, we are adding some vector, and this vector sorry, adding some weights, and these weights are belonging to 0 to 1, right? This could be either 0 or 1, both. Sorry, like this gamma comma 1 minus gamma, both of it will be between 0 and 1, that is they both are fractions. So what, just the conclusion is like the original data set should have higher the entropy. So which of the following condition must be satisfied for pure node? So pure node implies impurity is 0, right? Okay. And I have explained that information gain can't be negative. Why? Because the entropy of the original data set will be always greater than the entropy of the combined, and both the entropy of the combined data set and entropy of the original data set are positive, right? Like this is also positive, and this whole thing you are seeing here, this is also positive, but this is greater than, this thing is greater than or equals to this thing, right? So this information gain could be either positive, this information gain could either be 0 or it should be positive, it can't be negative. Remember this. Okay, so this is wrong. The entropy of the node is maximum. Like for a pure node, this is wrong. All samples at a node belongs to the same class. Yes. Then drop all samples at a node. Okay, so this is pure node, and in case of pure node, all the samples belongs to the same class. This is true. The entropy of the node is 0. Yeah, because this is pure, so impurity is 0. That's why entropy is 0. Yeah. Okay, okay. Another question related with the linear regression and the like. Uh, this question is on the variation of regression. So if you recall that we have three kinds of, not like the vanilla version, or that is the base version is the linear regression. Then for if there is like curvy boundary. Curvy decision boundary, then we moves to kernelized regression. and to handle the overfitting case, we have introduced the lasso and ridge regression, right? And while solving this question, the very first question I have explained, like the idea of linear regression is just to find this parameter w1, and the idea of ridge regression is to find the means to bring the coefficients closer to zero, and the lasso is to bring most of the coefficients to exactly zero, right? So this is the point. So if we try to analyze this thing, like we could see that this vector, this the components in this vector is like either close to -1. You could think like a close to -1 or point 0.9, or yeah. So we can say that this all the components are relatively bigger as compared to W1. Yeah. So W1 is kind of closer to zero with respect to this W2. So W1 must be something like a ridge regression. W2 will be the vanilla case of that is the linear regression, and W3, as we could see that some of the components are exactly zero, so we could opt for lasso regression, right? So W3 is lasso, and W2 is linear regression. So this should be the answer. Okay, like uh, this question is related with the clustering. I think it is in week 3. Okay, so the idea of the clustering is like you initially you have this data set, right? So first of all, remember that it is an unsupervised problem, so we don't have labels. We just have xi. So this thing is xi only. Yeah. So this tuple is like x1, this 3 3 is x2, this 3 4 is x3, and so on, right? Okay. Okay. So we have reached to certain iteration number like t. Okay, so let's go through the question. So suppose we want to cluster form 3 clusters, right? So this is classical k-mean clustering problem. Like k means clustering one, and here k is given to be 3. So we have to classify all the points into 3 clusters. And the first iteration. So we performed the first iteration and found that the clusters came out to be this point, these things, right? The current clusters look something like this. Now the question asks for what would be the second after the second iteration, how the cluster where the data point 3 comma 3 will go to. Okay, so this is very kind of easy question. If I try to explain using a graph, like maybe a graph will help. Like the idea is very simple. Let's say there are some points, like they, there are some points. Say this is a point. Yeah, let's say this is something like this, uh, or maybe like let's say we have cluster like this, right? Then what we will do is we will calculate the mu, that is mean of each of these clusters. We will find mu, say this is cluster 1, this is my cluster 2, and this is my cluster 3, right? After finding mean of each of these cluster, I will for each of the data point I will try to figure out like is it this let's consider this point. So let's consider this point. So I will ask whether this cluster this point is, I will try to figure out this point is closer to which cluster mean, right? Whether it is closer to M3 or M2 or M1. If I find that no, it is like it is closer to some other cluster as compared to the current one, then I will just uh, assign this point to this cluster. Okay, what I mean to say is that suppose while comparing, I have this data point, and then I found all this cluster, and then after I start comparing this data point, like I find the Euclidean distance of this mu and this data point, and I found out that okay, this appears to be larger than this one. Let's say the cluster of mean is somewhere here, of mu2 is somewhere here. Yeah, so this is like smaller, so I will assign this point to this cluster. So that's the idea. You should go through the lecture one in order to completely understand this concept, but I have covered it in brief. If you have seen the lecture, then you might have to follow the steps that I have told. Now, okay, so after the first iteration, we have this thing. So we just need to calculate the average. That is mu. Let's say this is mu1, this is mu2, and this is my mu3. Okay. How we will calculate mu1? So we have this 1, 2. Okay. So my first data point moves to the cluster 1, and my second data point moves to cluster 1 also. So I will take average of both these data points. So what will be the average? 3 plus 3. It's like 3 plus 1 equals to 4. 4 divided by 2, as there is 2 data points. So 4 divided by 2 is like 2, and 2 plus 3 is like 5. 5, and this is 2.5. Simple average. Okay. So this becomes my mu1. Similarly, I will calculate mu2 and mu3. So 3 plus 5 is like 8. 8. 8 plus divided by 2 is like 4. So we have 4, and we have 4. 4 plus 4 is like 8. 8 divided by 2 4. So this is my mu2. This is my mu2. And for this cluster 3, 7 plus 9 is like 16. 16 divided by 2 is like 8. And there is 9. Right? This should be the average. Okay, so this is my mu3. Now we have to check like this point is closer to which of these mu's. This data point is closer to which of these mu. So if you try to calculate the Euclidean distance now, then you will find like the formula of the Euclidean. So if there is say two data points, let me explain you the Euclidean distance. I think you know the point. So let's say this is my x1, x2. This is my point here, and there is some other point, say y1 and y2. So the formula of Euclidean distance is given as like we have to take the difference of both this, uh, both the order doesn't matter, like we have to take the difference of these coordinates and square it and then sum and then take the whole root, that is xi minus yi whole square plus x2, that is the second component, minus y whole square. We have to take this whole root, right? So by this we could find the Euclidean distance. So if you simply try to analyze, like 3 comma 3 is definitely much more, like see, the difference of first coordinate with respect to the mu1 is like 3 minus 2 is like 1, and 3 minus 2.5 is like 0.5, right? Okay, and then if we will try to find out the Euclidean distance, so what I will do is like 1 square plus 0.5 square, and then we take the root. Taking root or not taking root doesn't matter. You just need to compare the stuff that is within the under root. So like you just have to have the sum of square of these things. So you will find that this 3.3 is closer to m1. So this point will go to cluster 1 only. So there will be like no change. This assignment is correct. So the correct answer is cluster 1. Okay, I haven't solved this question till now. Okay, in case of ensemble learning, okay, see, in case of ensemble learning, this is called as like ensemble learning. This is called as ensemble learning. So the ideas of ensemble learning is like we have some weak learner, like weak learner. We have some weak learner. Yeah, we have weak learner, and we want to develop some strong learner. And from how we could go from weak learner to strong learner, there is two methodology that is sir has described. Number one is like the bagging, and the other is boosting. So in case of bagging, the idea is like you are taking overfitted model. You are taking the overfitted model, and you try to take the average of all the learned classifier, right? And here the weak learner is those who can predict like who can predict a slightly better than random guessing. That's the point. So like weak learner is will definitely perform slightly better than random guessing, and that's the point, right? This is the point. Like weak learner are those learners which could perform slightly better than random guess. Like random guess will be like 50% correct, but the for weak learner it will be like 60 to 65 something of this percentage they will uh, uh, classify correctly. Okay, so you should learn you the most important here is the the most important algorithm is the ADA boosting algorithm. ADA boost, ADA boost algorithm. This is very important. Market. This is like one question will be there from this concept only. Okay. Okay. Given a data set of the given point is given. Okay. Okay. A set of data point is generated from the following process. Okay. So this is like the underlying process or the underlying structure of the data is given. Hmm? And this error comes to be from Gaussian noise. Like uh, you so there was a question earlier also. Like I don't remember. I'm not recalling the exact. It's like around week 5 or 6 that yeah. So we we were trying to understand the probabilistic view of this error in most probably in the linear regression problem. We are trying to let me see just yeah. Yeah, in this lecture video you will find. So what in this video was discussed is like this epsilon is comes from Gaussian. So this y will also come from Gaussian, such that the mu, that is the mean will be this whole stuff, and the variance will come from this epsilon, right? Like epsilon have follows normal 0 comma sigma square, then y will follow normal of this whole stuff will be copied here, and it will follow the same sigma square. And I have to manage my mouse, that's why the handwriting is so tight. Okay, so here the question is not related with the linear regression. The question is related about either there is given two models and we have to understand like which cases about overfitting and which cases of about underfitting. So you should remember that like in case of overfitting we are assuming that the underlying structure is very complex. Okay, so there is see in the in I have discussed in the lecture also, like there is maybe the actually the relationship between this or like xi and yi is like something of this sort. But in case of overfitting we will say, oh okay, so we will try to exactly match the data point. Like we have data point like this. Okay, we have data point like this. So so this is like kind of sinusoidal, and but in case of overfitting we will try to exactly match the point. exact, yeah, so we will try to exactly fit the point. So this data is much more complex. This is complex, right? This is complex. So this structure is much more complex, and this is the case of overfitting. Overfitting, like in case of overfitting, what we do is that, so whenever we are making some prediction, right? Like whenever we are making some prediction, maybe the actual point is like here, but we are predicting here. Okay, so this is my error. This is my error. Okay, so in case of overfitting, we what happened is that we try to fit this error also. Like if this is not the ideal case, we should not fit error. Okay, but think now, like you have the data set. Okay, you have the data set, and then you don't know what is the underlying structure. You are just like kind of uh, try to figure out what is the structure. So try to came out with this exact structure is kind of impossible, right? We have to depend on the data point that is given to us. So one could come up with this very kind of complex structure. Okay, so this might be our structure. So but 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 we should have to keep in mind that there should be some noise also added while generating the data set. So we have also fitted the noise in this case. So this is a typical case of overfitting. While in case of underfitting, we assumes that like the data set is, means we try to came up with a model which is kind of simpler than actual. So if we came up with a model that is simpler, like kind of linear, or maybe like somewhat simpler than this original like sinusoidal problem, then this is case of underfitting. So in case of overfitting, always remember that there will be higher variance. Higher variance means if we change the data set slightly, like if the some like there will be some shift of point like this, right? There is some shift of points. So then the model will differ a lot. The model will differ a lot. So maybe for the here, for this means like for this point, earlier the model prediction was here, but now the model predicts here. So you can see that there is very high deviation. So this refers as variance. While in case of this is while in case of underfitting, you will notice that this variation is very low. This variation is very low. This variation is very low. Like the another model you came up with is like this, maybe of this sort. Okay. So for like we try to see. Actually, you might think like this is very high, but this is not very high. Like this, if we try to draw the diagram, then this is like this, it's like this. So variance is very low. While in case of the overfitting model, the variance is like okay, as like this, like this. So here the variance is like this. So here the variance is very low, but in case of overfitting, the variance is very high. Okay. So if you try to understand the form expression that is given, so we have like actual structure is of cubic nature. We have highest power of xi to the power cube, right? But in case of model 1, we are assuming that okay, it is a linear structure. We have a linear expression here, and in case of model 2, it is coming up to be an polynomial of order 5. So this is definitely a complex structure as compared to original one. So this should be of overfitting. This should be of overfitting, and this is this is lesser than that of the actual model. So this is the case of underfitting. Okay, and in case of underfitting, there will be higher bias. So the bias will be high in this case of underfitting. Okay, and in case of overfitting, the variance will be high. In case of overfitting, the variance will be high. Okay, so in the lecture, it is not given the actual drawing of the bias variance trade-off, but if you search in if you search what is bias variance trade-off, then there will be a curve of a graph will be shown of of this some of this sort. Uh, yeah, so this represents variance. This represent variance. This represent bias square. Okay, bias square, and this is our model complexity. This is our complexity of the model. Okay, so what this graph try to explain is that as we if our complexity is very low, then we have higher variance. This is the variance. So we have higher variance. As our complexity increases, the bias reduces, and our variance shoot out variance try to grow exponentially. So both of this curve is like exponential curve. This is exponentially decaying, and this is exponentially means rising, right? So somewhere here we could see that we achieve the minima. Somewhere here we achieve the minima. So if we try to draw the resultant of both this graph, the actual graph will be somewhat like this. So you can see that this U curve, right? So at some point of this original data set, you could notice that here in this region, the variance is also low and bias is also low. Okay, this resultant curve reflects nothing but our error. Okay, so error is, see, the error is nothing but the sum of bias, nothing but the sum of bias and variance. Okay, so if we this thing is constant, this error is constant for a given data point. For a given data point in our data set, this thing is constant. So if bias will increase, then definitely variance has to be decreased, and vice versa, right? See, I am talking of this graph. We could see that the model complexity is like optimum. Neither the variance nor the bias have very high value. Okay, so as this may not be asked because in the lecture it is not discussed, but you should have an idea that higher variance implies lower bias. Okay, okay. So tell me the answer. Like model one will have higher bias, yes, because it is underfitted. Then model two, yes, it is true. Now model two will have lower variance. No, it is overfitted model, so it should have higher variance. So this is wrong. Model one is more likely to underfit. Yes, definitely. and model 1 is more than zero. So it's that. Okay, so this question is from soft. Yeah. So this question is from soft margin SVM problem. Okay. So I think you should go two to three times about the derivation of like how things have came, and there are certain points like you should know what's the dual problem, what's the primal problem, and what is the complementary slackness condition for both the soft margin SVM and the hard margin SVM. Right? It should be on like fingertips. The concept should be on like fingertips, and the idea is not that hard. Yeah, you may think like we formulate first of all the primal problem, then we use the Lagrange multiplier in order to convert to dual problem, and then from primal and then dual we used to derive the complementary slackness condition. Like so, you may think the overall percentage means the overall derivation to be like some combustion, but uh, the idea should be clear. You should go two to three times that portion. I have visited about 4 to 5 times that portion, the derivation and all that stuff. Okay, so let's go to the question. So if alpha star is equals to C, okay. If alpha star is equals to C, okay. So recall that in case of soft SVM, so this question is worth discussing. Yeah, like see. So if you recall the dual problem, uh, as far I could recall. So it's like max over, is it visible? Is it visible, brother? Tell me. Okay. So it's like why so it's like max over 0 to there is some alpha and there is C. Right. So this is the hyperparameter that we need to figure out using cross validation and all that stuff. So this condition is known as the box condition, or yeah, this condition is known as the box condition. Like here the alpha is kind of boxes between 0 and C. This is 0, this is C comma C, right? In case of 2D, in case of 3D, it will be like a cube of length C, cube of length C, right? That's why this is called as box condition. And yeah, it is like alpha transpose 1 minus like uh, alpha times xy. It's like alpha, yeah, alpha y, alpha transpose y transpose x transpose x y alpha. Yeah, yeah, this is the dual problem. Now, now if you recall the complementary slackness condition for the soft vector margin, then it is like alpha star times 1 minus W transpose xi yi minus epsilon uh, should be equal to 0, and another is beta times epsilon should be equal to 0. These are the two conditions from complementary slackness, right? And in like first, let's try to dissect what the first point is telling. So it is saying that if alpha is c, okay, so alpha is maximum, okay, alpha equals to c is that like alpha is maximum. The ith point is incorrectly classified by the w star. Yeah, see, in case of soft vector machine, in case of soft vector svm, in case of soft vector machine, like this is our margin, and we have some positive points lying here, okay, some positive points lying here, some positive points are there, and some negative points are like this, okay, and the classifier, the linear classifier is, like this, okay. So this margin, this is like parallel, I mean not parallel, the both, this distance is equidistant, okay, this distance and this distance should be equal, like this, right, yeah, this should be somewhat of this sort. Let's draw some point. So this is case of hard margin as well, right? In case of soft margin, we allow some data points to mean, like we allow the outliers also. So there might be some outliers, like some of the positive points maybe could be here, or could be not be able to cross the margin, right? Or others could be like here, not that much. There are some data points like here, and maybe this point is not be able to come up with means close, jump the margin. Here is the data point. So alpha star will be the maximum, that is remember, always remember that alpha could go from 0 all the way to maximum of c. So when will be alpha equals to c? For those points, the alpha is nothing but the weightage given to this data point, right? Like if the data point is either wrongly classified, if the data point is like wrongly classified, then we will give them the highest weightage. So which points are the wrongly classified? Like if you try to figure out using this data set, then you could you find like which points are wrongly classified? Or see, for C there is two condition: either it will be wrongly classified, or it will not be able to clear off the margin. What I means to say is that for negative data point, see, the negative data point should lie, uh, the negative data point The negative data point should lie in this region, that is in the left side of this margin. Like in ideal case, this should be in the left side of this margin, and in case of for the positive data points, the positive data point should lie at the right side of this margin. That's the ideal case. So with this like sorry, let me say it again, let me read again. Forget everything. The negative data point should lie in the left side of this classifier, ideally speaking, and in the and the positive data point should be on the right side of this classifier. Okay, but in case of hard margin, we will say that okay, I will not allow any data points to be in this region. I will not allow any data points to be in this region. That is the case of hard margin SVM. Okay. In case of soft margin SVM, we said that okay, if the data point is like some data points are here in this region, that I could allow, and even if they are like outliers, then also we will allow. But the point is like in order to be get classified correctly, this data point have to pay some like price, like some penalty. The penalty, this guy should pay some penalty in order to be classified. So if you try to understand like which point is like kind of absurd in the sense is like wrongly classified. Okay, so if you will notice that like ideally this the negative should be in the lower this region. So this negative point, and this negative point is wrongly classified for the negative data labels, and for the positive data labels, thing these three data points are wrongly classified. So for this 1, 2, 3, 4, and 5, for these 5 points, the alpha should be exactly equals to C, and all the data points that is like on the support vector. So this is my support vector, this line is my support vector, and this line is my support vector. So all the data points that lie on the support vector, here point could be either C, or it could have a value of either 0 to, or it could be even any value between 0 and C. Okay, so we are not able to tell what exactly the point is, means what value what weightage should be given to this data point. So this for this, like what I am saying is like for this data points, for this data point that is lying on the support vector, this for this data point that is lying on the support vector, this the weightage should be between 0 to C included. Okay, so this is like third bracket. It could be 0, it could be C, or it could be any value between 0 and C, right? And similarly for the positive also, here the uh, alpha is nothing. Alpha is the weightage given to the data point in order to make the in order to determine the classifier, right? Like see, recall there is a formula of W star equals to sum of I over all the data points of alpha I xi yi. So this is nothing but this is I. Okay, this is not one, this is I. So this is nothing but this portion. This portion is nothing but the data point, and this is the weightage given to this data point. So we in order to figure out what's the W star, different weightage is given to each of the points. Like So which points are given which weightage? This question is related with that only. So for alpha equals to C, what a point is incorrectly classified by W star? Is it like, yeah, the ith point is incorrectly classified by W star? Okay, yeah, this could be case. This could be a case like we could see here also. We could see here. W star means the classifier is wrongly predicting the plus. Okay, the plus means there could be a plus that is lying in this region also. Okay, there could be a plus that lying in this region, in the left side of the classifier also. No problem in that. Similarly, there could be minus a here also. Okay, so this is correct. Alpha equals to 0. So always remember that the points which are correctly classified, the points which are correctly classified means correctly classified, but classified with sufficient or greater than margin. Like for the data, for the positive data point, this stuff, these data points will have a value of this this points will have a value of alpha equal to 0. Means these points will not contribute in order to determining the classifier. Okay, if alpha equals to 0, the ith data point is correctly classified. This should be correct. If the ith data points lie on the uh, the ith data points lies on the supporting hyperplane, then alpha equals to 0. No, no, it could be 0. What I have said, it could be 0. It could be anything value between 0 to C, or it could be C even. So if it lies on the data point, then it is 0. So this is wrong, right? It could be 0, but then all it will always be 0. This is not right. If the data point lies on the supporting hyperplane, it does not uh, pay any bribe. Okay, this is correct. This sounds correct. And if the ith data points lies between the supporting hyperplane, it always have it always have to pay a positive price. Yes, definitely. Like for see, if for this uh, positive point in it should ideally be like here also. So in order to move from this position to this position, this positive point has to pay some price. So this is also correct. Like so 1 2 and so A B and D E should be correct. Like let me see. If alpha star equals to C, the I data point is incorrectly classified by W star. Okay, okay. So there is a trick. There is a trick in this question. There is a trick in this question, or maybe I got tricked. Like, see, for alpha equals to C, for alpha equals to C, there could be either two cases. Like either it either it is either it is wrongly classified, means that is either it for positive data points, either it for positive data points the data points that will have alpha equals to c will lie on this region, on this note carefully that for data point for alpha equals to c, this thing should lie in this region. The positive data should lie in the left of this vector, strictly left. Okay, strictly left, not even on the hyperplane, not even on the hyperplane. So this region, and some of the data points on the hyperplane could be c also. Okay, so the I data point is incorrectly classified. For this thing, we could say that okay, this is incorrectly classified. But for those points that is lying on the supporting vector plane, we must agree that they are correctly classified, right? So if alpha equals to c, the point is incorrectly classified always. So the answer is no, right? It is not always that it is incorrectly classified. It is correct. It might be correctly classified. Like for the data point that is lying on the hyperplane, it could be correctly classified. For that reason, this is wrong. Okay, so this question is from perceptron. Okay, so we have given three, one, two, three. Yeah, we have given three data points. So it's like one, one. So we have here one and one. So we have a data point like here with positive. Okay, we have one, one, comma positive, and then we have 1 comma minus 1, 1 comma minus 1, 1 comma minus 1, and this is negative data point. And then we have minus 1 comma 0, like some point is like here, and this is minus 1 comma 0, this is minus 1, minus negative data point, right? Okay, so the perceptron algorithm is applied with the data set with initial vector of 0 0. Yeah, nothing new. It's the perceptron algorithm always initializes with 0 0. There is nothing new in this case. So while looking for the mistake, cycle to the data point from left to right. Okay, we will move from left to right. Which of the following statements are true? Okay. So first of all, for the perceptron algorithm, you should remember the algorithm itself. Like the algorithm is very simple. Whenever your current WT, okay, whenever your current WT is making is predicting wrongly for a data point. Let's say this WT, let's say this WT makes a wrong prediction for xi. Okay, makes a wrong prediction for xi, yi, makes a wrong prediction for xi, yi. Then it will be then the updated WT will be WT plus xi into yi. So this is the formula for perceptron algorithm. And you must note two things, like there could be some case like see, maybe say there is some data points like this. Okay, there is some data points like this, and there is some minus like this, and your current WT is and your current W is maybe like this. Okay, and it happens that for there exists one, this, okay, it happens that there is a positive data point that lies on the left of this classifier. So in order to accommodate this positive point, the perceptron will the perceptron algorithm the perceptron algorithm will try to adjust, and it may come up with something of this sort, right? Like here the positive points was there, and it will try to come up with this kind of classifier, like yeah, may come up with this kind of classifier when now this is making a wrong okay, think of it like this comes with this type of classifier, right? So earlier this yellow one is making a correct prediction for this data point, but in order to accommodate this correction, it changes, and now it's making wrong prediction with respect to the earlier points, but it is rectified for this data point, right? So what I mean to say is that for adjusting local choices, for adjusting local data points, it may happen that the perceptron adjusts in such a way that it now makes a wrong classification for earlier data points which are correctly classified, right? So you should always, suppose you got WT plus 1, suppose you got WT plus 1 after visiting this data point, and this is my WT plus 1, right? Then for this WT plus 1, in order to convert, you have to again check for all the data points. You have to again check for all the data points whether it is correctly classifying or not. Remember this point very importantly. This may come in question in some of this typical way or in a tricky sense. Okay. Okay, so let's back to the problem. So we have this data point and it is saying the algorithm will converge to W equals to 1 1. So there are a couple of questions with converge related with convergence. Okay, so let's see where it will converge. So earlier, yeah. So can I copy this whole stuff? Okay, okay. Let's try to solve it. So we have this data point. Let's write it once again. What is this plus one? This is one minus one minus one. So we have now 0 0. We have currently now 0 0. And what's the formula? What the formula is for for wrong classification, we will update the weight vector as the previous weight vector plus xi yi. Okay. So if we have 0 0 as my current WT, if 0 0 as my current WT. So how this WT will make prediction? Do you know? Like I have some classifier 0 0. Okay. So how that classifier would look like? Would you like would you able to guess uh, like in that lectures we have seen that generally classifier looks like something of this sort, right? But how the 0 0 vector will look like? So it will look like nothing, like it will have no magnitude, right? You have studied that in physics of class 9 also. So we have WT, and how it will make prediction is like it will take WT transpose WT transpose X, and if this thing come out to be, if this if this okay, okay. So the classification is like this. It will take sign of this value, and this is my WT is my initial not initial, it is my current like classifier, right? It's my current classifier. So the it is if this is 0 0, so the 0 0 dot product with any vector will give 0. And for signum we know that if it will this function will be positive if the this value this underlying value is greater than or equal to 0. Okay, so for all the thing it will be 0, so the prediction will be plus here and plus here also. Okay, but we could see that for these two data points it is making wrong prediction, so we need to update the WT. So now for this data point it will be WT plus 1 will be, it is earlier my it is 0 0 plus what is xi? Xi is 1 minus 1, and xi, and what is yi? Yi is the original data point. Okay, So it is my minus 1. So what will be the answer? So minus 1 into 1 is like minus 1, minus 1 plus 0 is minus 1, and this is 1. So my new wt plus 1 turn out to be minus 1 and 1. Okay. Now if you now this is my new wt new wt plus 1. Now let's try to understand how this performs on this data set, right? So we will take the dot, like now we will have wt plus 1. Yeah, so why not just call it wt, why not just call it w1, right? So it's my w1, it's my w1. So w, here we will write, here will be like w1 transpose x, and we will take signum of this in order to predict. Okay, so we will take the dot product of this. So minus 1 into 1, so like minus 1, minus 1 plus, plus 1 is like 0. So this will be positively classified. Okay, this will be positive for w1. I am doing for w1. So the first data point will be positive. Okay, and for the second data point minus 1, and then again minus 1. So it's like minus 2, and for negative it will be classified as minus 1. Okay, this is also correctly classified. And for this minus 1 and 0, for this minus 1 and 0, it will be like minus 1 into minus 1 is positive, plus 1. So it is showing positive, but it is actually negative, which means we need to again update this w. So my w2 will be, what's my initial w1, what's my initial w1, it's minus 1 and minus 1 plus, what's my xi brother, it's like minus 1 and 0. What's my yi, it's minus 1. Solve this. So it's like 1 and 0, we will add to get 8 0, there is 1. Okay, now this is my new w2. I will again check for all the data sets, right? We will check for all the data sets whether it is giving right prediction or not. So w2 is 0 and 1. So dot product, so 0 and 1, the answer turns out to be 1, and this is positive, this is okay, this is minus 1. And see, we are just taking dot product of this stuff with this stuff. Okay, so 0 multiplied by 1 is 0, and then 1 multiplied by minus 1 is minus 1, which is negative. So the prediction should be negative. Okay, okay, and this is 0 and 1. So this is this turns out to be 0, and also turns out to be 0. So it is, the answer is coming out to be 0. So signum of 0 is like plus 1, but it is minus 1. So here again we are doing wrong classification. So again we need to move to w3. So w3 will be the initial w2 plus, what is that point? It's minus 1 comma 0, minus 1 comma 0, and what is the actual vector? It's minus 1. So it will be like plus 1, and this is plus 1. So it will be 1 comma 1. Okay, so w3 turns out to be 1 comma 1. So again we will take the dot product, like 1 plus 1 is 2, 2 for 2 this is positive, this is correct, and 1 plus 1 is this 0 for this, then it is making mistake here. Okay, it is now making mistake here. and 1 comma 1 this is minus 1, and this is correctly classified, but this is now making mistake with respect to this data point. So what's my data point? It's my 0 and 1. What's the y label? It's minus 1. What's the initial vector? It's 1 comma 1, and this will be my w4. Now taking the product, so it will be minus 1 into 1. So this is minus 1, this is plus 1, so it is like 0 comma 2. This is my w4. Now again we need to check whether we are doing correctly or not. So 0 and 2, so the answer turns out to be 2, and for 2 it's positive, it's okay. 0 and 2, that's minus 2, minus 2 for negative, it's minus 1, okay. And then we have 0 and 2. So again this is making a wrong classification. Let me check whether I am making any mistake or not. Right? Okay, so it will converge to 1 comma 2. Okay, so it is now making mistake with respect to the last data point, that is minus 1 comma 1, minus 1 comma 0. So we have 0, 2 as my initial w5, right? We have w5 plus the point is minus 1 comma 0, minus 1 comma 0, and the vector is minus 1. So this will be 1 and 2. Now this is my new vector, new w, and for 1 and 2 let's try to figure out. So 1 into 2 it's like 3, for 3 is positive, okay. 1 into 2 it's like minus 2 plus 1 it's minus 1, and for minus 1 this should be no, negative, okay. And the 1 and 2, so this will be minus 1 into 1, it's minus, and for this it is minus. So yeah, it's all the data points are correctly now classified, so this will be my answer. Okay, so what's my parameter now? It's my, the parameter is my 1 and 2. Okay, the model will predict plus 1 for the new data point, 2 comma 1. Okay, so we have 1 and 2 as the wt, and we are predicting for this data point, so we will take dot product of this, so it will be 2 minus 2, right? 2 minus 2, this and that turns out to be 0. Okay, that turns out to be 0, which means it will be positively classified. Okay, that's correct. And the model predicts minus 1 for this 2 comma 2, no. So this 2 should be our correct answer. Let me see. Yeah. Okay, so from question 11, and there is one more question, right? This kernel one I will discuss very shortly in the coming video. Okay, thank you. Thank you, guys. So if you are liking the content of my channel, please do consider like and subscribing my channel, and if possible try to contribute very small amount such that I may able to buy the pen tab for myself. Okay, so thank you. Let's see again. Bye.